right, any other homeworks to turn in? Anybody else? Got everyone's homework? Cool. All right, questions on the homework?
My question's about number 6.
Yeah.
Yeah. I was doing. I didn't really get super far in this one. I was doing some digging through the book and online, and everything I could find about proving divisibility referenced induction.
Okay.
And so what I did on this one was I lined up n times n plus 1 times n plus 2 times n plus 3, and then I had factored it out and got a 4th degree polynomial expression.
Okay.
Then I was kind of shaky on where to go. I knew I needed to like reduce that modulo 6,
Right.
but I wasn't really sure on how to do that exactly.
Okay.
Yeah.
Anybody else have comments or experiences with this problem?
Pretty much the same.
Same
I
thing?
did the same thing, I just didn't multiply it out.
Okay.
I kind of did like a less logical, or more like logical idea where since mod 2 and mod 3, there's only 3 possibilities.
Okay.
And if they're all in a row, you know that one of them's mod 0, which means it's divisible.
Okay. Excellent intuition. We can make that rigid too.
But yeah, that was my problem. I had a hard time making that into a rigid proof.
Right,
And
but
I
that's-
was a lot of words, and I was like,
Yeah.
I was having a very hard time making it.
Okay, but that's the right intuition. And then the question is, how do we rigify it? So, do you have a comment?
I mean, I'm wondering if I didn't do it wrong now, but what I ended up coming up with was where you would, you know that 2 and 3 are factors of the resulting product. So because 2 and 3 are factors, that means that 6 is also a factor,
Correct.
which means that the whole thing's divisible by 6.
Right, so if we have n plus 1, n plus 2, n plus 3. So you're saying one of these has to be divisible by 3, and 2 of them have to be divisible by 2.
That's what I was going for.
So as long as you know that, but 2 of them could be divisible by 3 also. So the danger is, could the same 2 that are divisible by 3 also be the same 2 that are divisible by 2? And if that were the case, then you might not have divisibility by 6.
Well, but if 2 and 3 are the prime factors of 6, isn't that not a problem?
Yeah.
Well, for example, if I knew that this number was divisible by 2 and divisible by 3, yeah, then it would be divisible by 6. So that would work.
That would be a plus.
Yeah. Yeah.
Plus, there could never be 2 that are divisible by 3 and 2.
Right, because consecutive numbers divisible by 3, one will be odd, one will be even.
So that's kind of what the logic I was going with, where I set up 2 kind of possibilities. Either 2 would be even numbers and 1 would be divisible by 3. In which case, if you multiply the moduluses of those together, it would be divisible by 6.
Okay,
And the
cool.
other possibilities, one is 2 are even, but one of the evens is also divisible by 3, which would mean it's divisible by 6 is divisible by 3 times divisible by 2 is divisible by 6.
6, right.
So, and same thing, even divisible by 6 multiplied by whatever is still divisible by 6.
Cool. Yeah.
If we wanted to expand this even further, you could say that any 4 non-zero consecutive numbers, you could say also divisible by 24, because you have one number that's divisible by 2, one number that's divisible by 3, and another one that's divisible by 4. That's not divisible by the same number that's divisible by 2.
I believe that. Cool. Is there another comment over here? All right. Excellent intuition. This is better than what I was hoping for, which is to have have you think about this and play around with just the numbers of it. Logically, what does it mean to have 4 consecutive integers? That's great. I got no problems with any of those arguments. Let me show you a different way to show this directly using modular arithmetic. So we can break this into cases. N is going to be congruent to one of these 6 numbers. Modulo 6. And we're looking at n times n plus 1 times n plus 2
You mean
times n plus
n is
3.
going to be congruent to those numbers, or the product?
N itself is an integer, so it's got to be congruent to one of those 6 numbers.
Mod 6, okay.
Mod
yeah.
6.
Your first number has to be underneath 6.
So we can break this into cases. If n is congruent to 0, we know the product's congruent to 0. So this is going to be congruent to 0, and this is all mod 6. So if n starts off divisible by 6, then n times n plus 1, n plus 2, n plus 3 is obviously divisible by 6. If n is congruent to 1, then this is congruent to 1 times 2 times 3 times 4, which is 24, which is divisible by 6, so that's congruent to 0.
We could have just proved it by plugging in every possible.
Yep.
Oh, because it's modular.
Because it's modular, so we only have 6 cases to try.
Are you multiplying the n's by, or dividing the n's by 0 on that?
I'm multiplying n's congruence modulo 6 with n plus 1's congruence modulo 6.
Okay, I was just wondering, because you have that 0 underneath, I'm like, is that dividing it by 6?
Yeah, if this is actually 0 times 1 times 2 times 3, which we know is going to be 0, so that's congruent to 0.
Okay.
And now it's just a set of cases. If n is congruent to 2, this is congruent to 2 times 3 times 4 times 5. And this is divisible by 6, so this is divisible by 6. And you go through the other 3 cases, and you've proven it in all possible cases.
It's a lot simpler than I was making it up to be.
That's simpler, but not as insightful in some ways. That's just an exhaustive proof. I actually like the insightful proofs that we were talking about a few minutes ago of every other number is divisible by 2 and so on and so forth. But for other questions where, prove that the product of 2 numbers that end with a 1 ends with a 1, you can go straight modular arithmetic or things like that. If you wanted to prove that in any 3 consecutive integers, at least one of them is divisible by 3, you can do that in cases. If your number is congruent to 0 mod 3, you're done. If it's congruent to 1, then the number plus 2 is divisible by 3. If it's congruent to 2, then n plus 1 is divisible by 3. So cases help sometimes. Yeah?
I couldn't prove number 4 for the number is greater than or equal to 9 because it doesn't work for prime numbers and it doesn't work for 9. Assuming you limit yourself to odd primes. If you remove the odd primes limitation, you can utilize 2, which allows you to do every odd number. Greater than 7.
Might be backwards.
Right.
Well, actually, this approves to that because you can't get 7 with the 7 3 on the.
Yeah, 7 was a typo. It should have been 9.
Okay.
We did that the other day.
Okay.
I mean, it doesn't work for 9, though.
You can't write 9 as the sum of 3 odd primes?
No.
3 and 3 and 3.
plus
Plus
3.
3. It doesn't say they have to be different primes.
Right.
True. I didn't think of using 3 more than
Yeah.
twice.
Yeah. What about 11?
The 5.
1.
3, 3, and 5.
Yeah.
Right.
Well, I proved it for 7, so.
Okay. What about, so who else had some insights on this? Did anybody prove?
I kind of followed a logical path. I'm not sure if it's very rigorous though.
Yeah.
Yeah.
What you said made sense though, right?
Well, if you're assuming the Goldbach's conjecture is true, then every number beginning with 4 can be written as the sum of 2 even primes, but 2 is the only even prime. 6 can be written as the sum of 2 odd primes. 6 plus 9, or plus 6 plus 3 is 9. And from there you have every prime after 2 is odd. So if you're assuming that every even can be written as the sum of 2 primes, odd, parenthetical, then every number 3 greater than that, which is also odd, beginning with 9, can be written as the sum of 3 odd primes.
Cool.
That's kind of fun.
That's what you did. So it's almost a trick question. Let n be any odd number greater than or equal to 9. N equals 3 plus e, where e is greater than or equal to 6. 6 equals p1 plus p2 by Goldbach's conjecture, which we're assuming is true, or sorry, e is an even number, right? E is even, because n's odd and 3 is odd, so n minus 3 is even. So e is an even number bigger than or equal to 6, and therefore it can be written as a sum of 2 primes by Goldbach's conjecture. And so n equals 3 plus p1 plus p2, and that's n written as a sum of 3 primes.
And that would be a sufficient proof.
That would be a beautiful proof. You'd need to do a little extra work to make sure that p1 and p2 are odd, which was partially in your explanation already. If they're not odd, one of them has to be 2, and if e's bigger than or equal to 6, e minus 2 would be 4, and there's no primes that are even, therefore bigger. So you can wave your hands at that a little bit. So yeah, that would do it. And for bigger odd numbers, we could subtract 17 if we wanted, and we're going to get an even, and we can write that as a sum of 2 primes. So it sort of falls apart quickly. Other questions? You had a question on Fermat's Little theorem?
Yeah.
So,
7.
how did question 7 work out?
Nice.
Nice? I hoped it was going to work out fairly nicely. So we're trying to compute 23 to the 1002 modulo 41. Don't try it on your calculator.
Excel can't even handle it.
Yeah. It's a big number.
Google can handle it.
Wolfram can
Google can handle
Wolfram
anything.
can.
Wolfram can handle anything.
Well, that's 23 raised to the 40 is congruent to 1 mod 41. Yeah,
That's,
20.
that's not what he said.
25,
but
yeah, that's where it's.
Yeah.
yeah.
So we note that 1002, first of all, we use Fermat's Little theorem to tell us that 23 to the 40th is congruent to 1 mod 41. And that's the only thing we can do with FLT in this problem. And then from staring at this, we ask, is there a way to get a handle on this? And we say, well, 23 to the 40th is 1. 23 to the 80th is just this thing squared, which is also 1. 23 to the 120th is also 1. 23 to the 160th is also 1. And in general, 23 to anything times 40 is going to be 1. And so is there something times 40 that gets us close to 1002? And yes, 23 to the 50th, keep doing 50. 25 times 40 is congruent to 1. And that's 23 to the 1,000th. So 23 to the 1001 is just 23. And 23 to the 1002 is just 23 squared, which is something your calculator
529.
can do. What is it?
529.
And if you reduce that modulo 41, that's 12 times 41 plus 37. So this is congruent to 37. Or negative 4 if you like. Yeah.
How do we know all those are congruent to 1?
We know 23 to the 40th is congruent to 1 from Fermat's little theorem.
Yeah, but
This is just this squared.
oh,
You're squaring both sides, and 1 squared is still just 1.
okay.
Right, so we have this fact from algebra that also works for modular arithmetic.
So if it was, say, 23 to power 40 is equivalent to 5 mod 41, you would just square 5 by square.
Right, right. But with Fermat's little theorem, this is always a 1. So the
That's
power
right.
is, that's why it's useful for this, yeah.
Not in Fermat's whole theorem if we started with 23 to the power 10 instead of to the power 40.
Correct. It's gotta be p minus 1.
Does it say right there?
I mean,
Where?
it just so happens that 23 to the power of 1 mod, sorry, 23 to the power of 10 mod 41 does
12.41
equal 1.
30.
And then you raise, wait, what?
12 times 41. What were you saying?
If you have 23 to the power of 10 mod 41, that does equal 1.
Okay,
So if you raise those to the 4th power, that's not straight up for Fermat's theorem.
yeah, but that's
It
also,
happens to work.
that's cool. But you need a way to know that 23 to the 10 is congruent to 1, which your calculator can do, I'm guessing.
Right. It can do that.
Any other questions?
I remember on number 2,
Mm-hmm.
I was, I looked in the book and I found the different ways of what I was originally doing. But what I was doing is thinking of, like, say, 66 modulus 7 and seeing if that equaled 3.
Mm-hmm.
And I kept getting the same, I got the same answers as doing the, like 66 minus 3 mod 7.
Right.
Is that just, I'm like, is that now just a individual case or was that? how it-
So if this is congruent to 3, that means 66 minus 3 is divisible by 7.
Yeah.
That's another definition of congruence. So that should always come out like that.
Yeah, but outside 66 modulus 7 equals 3.
Right.
Okay.
Yeah, so this is exactly the same thing as this. Because if this is true, we can do algebra, we can subtract from both sides. And 66 minus 3 is congruent to 0, which means it's divisible by 7. And that can help with things like the negative 67 case, because now negative 67 minus 3 is negative 70. It tells you it's divisible by 7, so negative 67 is congruent to 3. Does that answer your question?
Well, what I was doing is, minus 67, and modulus 7 equals 3, like, when you type in the calculator.
Oh, you're right.
And that's what you get as the remainder is 3.
Okay,
I
right.
was just wondering if that's just kind of a way, in a different way of doing it. Or...
I think it's just a different phraseology, maybe.
Okay.
67 67 modulo 7 usually means what's 67 congruent to. And it usually means give me a number between 0 and 6. Anything else? All right, let's continue summations, matrices, and functions. I'm going to try to finish these up today and tomorrow, and at least get started on induction tomorrow. And so we're about 4 days behind the schedule, which is good because I had at least 1 week of slip time in the schedule, so we're making good use of time. My original syllabus weekly breakdown had about an extra week in there that I was going to fill in with whatever. And we're about 4 days behind on the original schedule, which means we'll be filling in that week nicely with stuff from earlier in the syllabus.
So you would say you're a glass half full kind of guy.
Yes. So we were talking about summations, basic concept of summations, the fact that if we multiply our terms by a constant, we can pull that constant out. The fact that if we add two summations, we can take the things inside and put them together, as long as the limits of the summation are identical, and so on and so forth. And we had finished talking about these geometric sums. So, and I think I was just doing r to the I, and I was ignoring a constant in the front. And we had calculated this and then calculated the sum up to n plus 1 and done some subtraction and came up with a cool little formula that I conveniently did not write down, but which I can reproduce in a second.
I've got it here if you want it.
Yeah, I have it.
Tell me if this was right.
Yeah, you're good.
Cool. All right. And this is a formula for a geometric series. And if r is something like 2, alright, so we're adding up 2 to the I. This is 2 to the 0 plus 2 to the 1. And this goes up to 2 to the n. And this formula here tells us that's actually 2 to the n plus 1 minus 1 divided by 1 minus 1 is 1. And this is a fact you should recognize from computer science. If you add up the first n powers of 2, you get the next power of 2 minus 1. And if you think of it in binary, this is the binary number. Well, if I write it like this, this is just the binary number represented by all ones. And it's always 1 less than the next higher power of 2. So this is 7, this is 15, this is 255, and so on. And so last thing I just wanted to mention is the idea of things like double summations. Where we might have some bizarre function of these two sets of coefficients. And this is basically just a sum of this thing. So we can expand that inner sum first and then the outer ones. So for example, sum from I equals 1 to 2, sum from j equals 1 to 3 of I plus j. And to find this, start off with I equals 1. And this inner expression becomes the sum from j equals 1 to 3 of 1 plus j. And then set I equal to 2. And this expression becomes the sum from j equals 1 to 3 of 2 plus j. And we want to add these together. So the sum from j equals 1 to 3 of 1 plus j is 1 plus 1 plus 1 plus 2 plus 1 plus 3. And then that second summation on the outside, the sum of 2 plus j as j goes from 1 to 3 is 2 plus 1 plus 2 plus 2 plus 2 plus 3. So that's a shorthand for this. And I don't think that's anything particularly meaningful for us right now. But in general, that's how you can do nested summations. I'm curious though. You see my fingers moving more?
So similar to like points on the screen.
Yes. Yeah.
Makes me think of nested for loops.
Mm-hmm. Exactly. Because we can think of a summation as a for loop, so this is exactly like nested for loops.
This also seems kind of similar to the set multiplication stuff that we were doing, where you would have
Combinations of
yeah
the Cartesian product.
Cartesian product.
Yeah, something from the first set, something from the second set, right? Because we're getting all combinations, and we could probably express some of those operations with this kind of setup. And everything's all the same as everything else in the end. So these insights aren't just coincidences, I don't think. All right, last thing I want to mention, and this may or may not be important in life, so it's up to you if you want to take notes. I think it is important in life. If you have a sum from, say, 5 to 10, we can always rewrite this using a pair of sums from 1 to something. For example, the sum from 5 to 10, that's A5 plus 6, 7, 8, 9, 10. That's the same as the sum from 1 to 10 minus the sum from 1 to 4. Because this will be A1 plus A2 plus A3 plus A4 plus 5, 6, 7, 8, 9, 10. And then we're going to subtract off A1, A2, A3, and A4. So these are exactly the same on both sides. But the nice thing is that these are summations that start from 1. And when you find formulas for summations, they're usually formulas that start from some fixed lower value. And we may not have a formula for the sum from I equals 5 to 10 of 2 to the I. But we know it's the sum from 1 to 10 minus the sum from 1 to 4, which would just be 2 to the 11th minus 2 to the 5th. So that can be useful for breaking down these expressions. All right, good on sums. Let's jump to matrices. And we'll see some uses for double summations in a moment. So we deal with matrices in 120. We deal with them at a fairly deep level. So that's 120.
Really touched on that, really.
Did I?
Oh, I didn't have you, I had some.
Oh, okay. I try to delve into these just because I'm a geek and I geek out on matrices pretty easily, but you also encounter these in other courses, and in particular if and when you take linear algebra, it's all about matrices. And they're popular in engineering, and they're really popular in computer science, and if you do computer graphics, that's all matrices. If you do robotics, that's all matrices. They're a really powerful tool for getting your handle on high-dimensional systems, like a 6-degree of freedom robotic arm, and you want to track its motion through space. You can do it with some matrix equations. So what's a matrix? It's a collection of numbers with a certain structure. There's a matrix. That's a 2x2 matrix. Yeah,
Why is it that these are brought up in a lot of classes but not thoroughly explained?
I don't know. That's part of why you take 215 though,
Oh, good.
because we do thoroughly explain them
If you're
well.
interested in matrices, you can take math too.
Yes.
Which is terrible.
Yeah, if you take linear algebra, that's what you do. Right? You'll go all through this. And that's why, that's usually part of an engineering curriculum. But they're so easy to use, but in some ways very tricky to understand sometimes. And so a lot of times we just use stuff without really understanding it. Like, I don't know how this marker works, but I know how to use it. So there's a matrix. It's a 2x2 matrix. This happens to have integer values, and one of them's negative. This is another matrix. So let me number these. That's a 2x1 matrix. So when we talk about dimensions, it's the number of rows and then the number of columns. And that matches a lot of programming languages. That's also a matrix. That's a 1x1 matrix. It's just a number, but we can call it a matrix. Here's a very special 3x3 matrix that's called the identity matrix. And we'll play with that a lot in a moment. So what can we do with matrices? Well, one thing we can do is we can transpose them. We can swap rows and columns like this. Instead of row 2, column 1, put this in row 1, column 2. And we just kind of reflect it around a diagonal line.
Wait. Well, why transposing rows and columns?
That's what a transpose, that's what this symbol means. It means it's M1 with rows and columns swapped with each other. So M2, I don't know if that's totally legal, but I swapped rows and columns. And it changed its dimensions. Instead of being 2x1, now it's 1x2. This I can call the identity matrix. And if I swap rows and columns, it looks exactly the same. That's a special kind of matrix that's equal to its transpose. Yeah?
So with matrices, is it kind of like a two-part array?
It's very much like an array, a two-dimensional array. And on a lot of languages, we actually sort of think of them as columns and then rows and then columns. line up pretty nicely. But matrices can have more than 2 dimensions.
Yeah, I know.
So could arrays, I guess.
How would you write that?
I wouldn't. I need my magic 3D BB to like make it pop out.
Or 4 dimensions.
Tennessee tuxedo reference. All right, so these are 2-dimensional matrices, various dimensions to them. So dimensions just the size, number of rows, number of columns. Some matrices are equal to their transpose, most are not. Yeah,
Can you transpose M3?
M3, sure.
So you can transpose any matrix then?
Yes.
There's no rules on, okay.
As far as I know, maybe there's some branch of something that says you can't transpose a matrix that's not square, but I'm not familiar with that.
It sounds like
So I think it's kosher.
how it is.
Yeah.
It is.
But that's not terribly exciting to just sort of transpose matrices. You want to do more than that. So another thing we can do is we can add matrices. And if we add matrices, they have to be the same size. And we do sort of the most painless thing we can imagine, which is we just add element by element. So 4 plus 4 is 8, 2 plus negative 1 is 1, 3 and negative 6 is negative 3, and 6 and 3 is 18. So just add each element. That gives you the element in the sum.
18 or 9?
I multiplied. Bad teacher. There we go, 9. Thank you. We can subtract exactly the same thing. 4 minus 4 would be 0. 2 minus negative 1 would be 3, and so on. And we can also multiply by scalars, things that aren't matrices, things that are just numbers. So, if I multiply this matrix by 5, multiply each element by 5.
Would that be the same as multiplying by a matrix, a 2 times 2 matrix where everything is 5?
I don't believe so. We're getting really close to matrix multiplication now. So we can add and subtract matrices. We can multiply matrices by scalars, just plain old numbers. And we can do combinations of those. We could take 5 times this matrix minus 3 times that matrix. And it's very easy. We just multiply the elements and add or subtract, and so on. The interesting stuff starts when we talk about multiplication. And multiplication of 2 matrices is not as straightforward, as you can tell by the size of my parentheses. So here's what we do when we multiply these matrices. First, we're going to try to find the value that goes here. And to do that, we're going to use the first row and the first column. So we're trying to fill in row 1, column 1 in the product. We're going to use row 1 in the first matrix and column 1 in the second matrix. And we're going to do what's called a dot product. We're going to say, someone's taking physics, 4, 2 dotted with 4, negative 6. And we'll talk about what a dot product is in a moment. Row 1, column 2, which is over here, we're going to use the first row, which will be 4, 2, and we're going to dot that with the second column, negative 1, 3. row 2, column 1, we're going to take row 2 from here, which is 3, 6. And we're going to dot it with column 1 from the second matrix, 4, negative 6. And row 2, column 2, we're going to take row 2 from the first matrix, column 2 from the second matrix, and we're going to dot those. So what is a dot product? When you have two vectors like this, a vector is a one-dimensional matrix. When you have two vectors and you dot them, you multiply in pairs and you add together. So it's going to be this times this, plus this times this, plus this times this, and so on. So 4 times 4 is 16. 2 times negative 6 is negative 12. That gives me 4. So that's row 1, column 1 in the product matrix. 4 times negative 1 is negative 4. 2 times 3 is 6. Negative 4 plus 6 equals 2. And so on. 3 times 4 is 12. 6 times negative 6 is negative 36. That's negative 24. And our last one, 3 times negative 1 is negative 3. 6 times 3 is 18. And that's 15. So our product matrix is actually 4, 2, negative 24, and 15. Assuming I didn't make any mistakes.
I think we did this in calc 3.
That
Maybe calc 4?
that could very well
No,
be.
it was calc 3.
Calc 3.
Calc 3.
How about we use the dot product for
Dot products pop up in physics all the time. You use them when you have a motion in 2 or 3 dimensional space and you want to do like F equals MA, you can use dot products to capture the 3 dimensions. So MATLAB, of course, can do this for us. So I can make a matrix A, which is 4, 2, 3, 6. I can make a matrix B, which is 4, negative 1, negative 6, and 3. And then I can do A times B, and I get 4, 2, negative 24, 15. And that's the way that MATLAB does this, is by doing these dot products for each position. And we can generalize this. We can write a matrix as A sub ij, and that means A00, A01, A02, A10, A11, A12, A. Let me start from 1. Because I want to go up to N. Alright, so our elements go from A11 down to ANN. And we can just write that as AIJ. And I'll just assume that this is a square matrix, so it's N and it's N over here. And if we multiply by BIJ, figure out what we're going to get in general. So row 1, column 1 is going to be the dot product of this with this. So it's A11B11 plus A12B21 plus A13B31. That's the upper left element of this matrix.
Wouldn't it make more sense that instead of have N's, just have I and J's? For column, or for rows and J for columns, we would have I number of columns and J number of rows.
Yeah, I wanted to keep it simpler. And I'm using I and J as indexes for each element.
Okay.
So in general, for the element in row I, column J in this product matrix, it's going to be the dot product of row I and column J, which is AI1 times B1J plus AI2 times B2J plus and so on, which is a sum from K equals 1 to N of A, I, K, B, K, J. That's what I wanted to get to. So the details aren't critical. The take-home message is we could write a summation equation for computing this dot product, and we could express each element in this product matrix, element ij, as a summation formula. And that's what you code up if you want to write a program that does multiplication like MATLAB. All right, so tomorrow I want to talk about why we care about matrices. Because we can use matrices to solve simultaneous equations, and that's the real connection. This is why playing with matrices sort of drives our society right now. All the good stuff that we can do comes down often to solving matrix equations. All right, so we'll talk about that tomorrow, and then we're going to talk about functions, types of functions, and properties of functions, and then we'll go on to mathematical induction, and then quiz on Friday.